I'm assuming there's going to be at least 3 more in the class. But so what I'll do is look at the weighting of test labs and the research project. Because the way it was before, tests were for it was 40%, or at 10%. So that was 40% of the 70% of tests, and then the final 30% labs and projects, is 30%. So the research project %, labs 16%, 8 of them at 2%. So these 4 tests that we have 2 done, I'll find out from Ryan if everybody's only coming back for 1 week. I don't know if you do 1 test and then the final test. So I'll talk to him about where we're at as far as if we got 2 of these are done. So we got a 20% of that 40% of tests are we change the weighting of them. To them we were 20% each. So if you look at it, if those 2 tests are done and they're worth 20% each, that's 40% of your final mark that has been looked after. Or 20%, 2 of them, so 40% of the project, 16%. And if you do all the labs, 40, 56, should go to 7. No, labs are 16%. So having done 2 tests, labs and research project, that's 7%. If things have gone decent up to now, if you've got, based on this, if you've done 7% average up until now, you'd be at 49, 70. You have marked at 49% roughly before you do the final test for the 30. So that's what I got to talk to Ryan about. I'm sure that's what everybody's scrambling, trying to figure out is how to keep the course outline. Tests were 7%, labs and projects were 30%. We have to keep that part as it's written in the course outline.
You're aiming for the final exam to cover those last objectives?
Yeah. Yeah. what we're going to look at today is transformers, single-phase transformers, three-phase transformers, current transformers. And then there's basically one chapter that has generators and controls and distribution. This one here, we've looked at electric calculations, AC theory of machines. We'll finish up with transformers, electrical theory and DC machines. So this chapter goes through the one-line diagram with multiple generators, generator panel, and all the meters. Then this chapter doesn't have the part about distribution. So basically, what we haven't covered after transformers today is chapter 9. So the final test will have chapter 9, transformers, and some of the other stuff that's on the test too.
But AC, are those going to be tested, or do have to one test?
We've had two tests, one on DC and one on AC machines. Yeah.
We did.
Oh no, sorry.
One of them we did.
Yes. The next test is going to be the following week.
That was easy. Right. Easy.
Right. Okay. Yeah, so the test will be an overall, it'll cover the tests that we didn't do, the information that within those tests. But nothing outside of what we've covered with the PowerPoints on Blackboard and what's in these 4 chapters. There'll be no surprises. It's all stuff that you have access to. And that Ryan was in touch, email-wise, with the instructors too, to see what you still have to cover and how we're going to do it with this not normal situation that we're going to finish up with. So that's what I'll be looking at, so that everybody at this state, at this time, knows roughly where they're at. If you look at this here, that marks-wise, we've got 49%. For 70% of marks done, if you do a decent job on the research project, the lab's finished in 2 tests. So that should, if you've done decent up till now, then there's not the pressure going into the final test that nobody needs after the past few months. Okay. So, if we look at what Pan Global chapter has, on transformers, it goes briefly through single-phase transformers and a little bit on three-phase transformers. But then we'll look at the Herman textbook PowerPoints that are specifically on single-phase transformers, three-phase transformers, and I don't want to mention current transformers in here. I didn't see where. transformer. Let's move it on power transmission. So one of the reasons the popularity of alternating current systems is the ease with it. AC voltage current levels can be transformed. Large amounts of power can be transmitted to high voltage and comparatively low current levels to be changed to lower voltages and higher currents in the locality where the power is to be used. The size of the conductor is proportional to the size of the current. Thus, such transmission methods affect large savings in copper costs. The device that makes this transformation possible is a transformer. So as far as transmission goes, we talk about from Bruce to Owen Sound. You're generating electricity at a certain voltage, which that's what I want to be part of the project, is to dig into it, find out what voltage it generated at. Then it's transmitted up to the switch yard where there are transformers in the yard, which change the voltage because now you're taking and transmitting a long distance. So if you can up the voltage, the current goes down, and you just need smaller conductors then. And in transmission lines, it's not copper lines; they're all aluminum conductors. So the higher the voltage you can bump it up to, the lower the current, the smaller conductors, the further you can go. And that's like I said, is the advantage of alternating current. It's easy to transform it, bump it up or down. DC, you don't have that option. They're talking about high voltage DC transmission lines. I've read a little bit about it, but I'd have to look into it more. Because most of what we use other than lighting stuff, how much DC do we use now? Laptop, phones, anything that's rechargeable now, everything's operating DC. You're using AC to change it to DC. But as far as transmission, that's where AC shines and transformers are used all over the place. So if you're driving down a lot of side roads, secondary roads have distribution yards where you'll see it. The higher up on poles, you see transmission lines that's usually higher voltage. And you'll see that the higher lines will come and they'll be dropped underground usually, and then into the transmission area. And then there'll be lines leaving there. In that case, they drop in the step down transformer from high voltage to lower voltage where you can use it in the area. So when you start at Bruce power, generation voltage, out to the switch yard, and then it's changed so you can go a longer distance. You get to the Owen Sound area, there's a transmission yard where it will change voltage again, so it's in the city for the factories. They can take a higher voltage because they have their own transformers that they bring it down to for the voltage that they use in their plants. Some plants use 4160, 4160 volts. I think over on some of the ski hills. I'm not sure what equipment, but when I was at an art flash seminar, which deals with the potential for harmful or flash if there's a fault. There were some guys, they're employees from one of the ski hills. They have draw breakers where you have to crank them and make sure they're de-energized. They crank them out, they do maintenance, they put them back in again. But they were 4160. They said that they are doing it. So if you have equipment that's 4160 in your facility, internally then, you will have transformers after that to bring your voltage down to 600 volts, which is a very common voltage for motors. One phase and a neutral in a 600 347 system is used a lot of times for lighting. Some lighting in this building is 347. And then from 600 to 208, that's what we have in the workstations. So that whole workstation is 208 volts if you have the 3 phases, and 120 volts if you have a phase and neutral. So transformers are all the way through from Bruce power to the outlets in this room. It's at every step, whatever voltage is best for that use, you can take a transformer and make it happen. Yep.
You mentioned about why would they bother about high power DC? What would be the value? Is there that many losses changing everything?
I'll dig up the article that I was looking at, and we'll see. It's in one of those electrical business magazine I get monthly. It's in the electrical lab. I bring them in and I just leave there. There are some neat articles in them. And I'll dig it out and see exactly the details of it. It's not common, but they are starting to.
Well, I know with like electric cars, I think they need to be DC to charge, right?
Yeah. Yeah.
There might be a bigger load time, but why would you transmit it AC so easy to do?
Yeah. No, it's a good question. And
high voltage DC, I kind of transmit less loss than the DC.
Oh, okay.
But the problem with stepping it up and down.
Yeah. Yeah, you'd have to have an inverter or converter. When you went from DC to AC, it's a converter. You go from DC to AC. AC to DC, one way or the other. Because a variable frequency drive is called an inverter. You use it on motors, on 3-phase motors. So stepping up and stepping down is just a matter of the number of turns of wire that are on one side of the transformer compared to the other side. It's directly proportional to the turns, whether you're stepping up or stepping down. I'm in a situation on a project where we talk about generators too, but they bought a used backup generator for the facility that we're going to install. And they're building the system voltage is 600 347. And he bought this generator off the Gigi from a guy who told him, yep, it's 600 volt. And we got this pretty big generator in a trailer, and it's got all the ventilation and louvers and everything in it. And the nameplate says 208 volts. So he went back to the guy he bought it from and said, no, it's not volty, and should have looked at it, went and looked at it first before you spend $20,000 or whatever. So we ended up getting a transformer to change it from 208 to 600. It's this wide, this high, and that deep. It's huge. So we have to figure out what it takes now to put this transformer at 208 volt generator to supply 600 volt 3 phase into the building. There is a problem that we may run into. A step-up transformer is different than a step-down transformer. And what he got is a step-down transformer. There's 600 volts in the primary, intended to give you 208 volts in the secondary. But he said, well, just reverse it, put 208 volts in the secondary and you'll get 600 in the primary, which in theory you would. But we looked into it. My son pulled up a paper, a technical paper written by GE, I think. And it says there's huge potential problems doing that. He might not, but he might. Because when you turn power onto a transformer, there's an inrush of current. At that instant that you're, and it'll talk about it when we go through the PowerPoint stuff, but for an instant there's an inrush current. And it can be 3 to 6 times what the current is in the system. You have to account for that with fuses. So if you've got 208 volts coming from the generator that's going to the secondary side of the transformer, the way it's built, you're only allowed 300% using above what the nominal current is for that transformer. But if you can end up with more than that inrush, because it's secondary and not primary, you may have to increase conductors and fuses, and then you're not code compliant. So it's going to be interesting trying to figure out what happens.
So it has protection on the primary side for to deal with this inrush, but not on the secondary side. Is that how that works?
It's the potential for the 208 volt side to have like 1200 amps inrush.
Right, but I'm saying there's protection on the one side that's designed, because it was designed in a specific way, it has protection on one side, as opposed to the other side where it doesn't.
You have to have fusing on both sides anyway. But the maximum you can go on the primary side of the transformer is 300%.
Right.
And it may require more than 300% to account for this inrush.
Would it have been designed to deal with the inrush?
It wasn't designed to be a step up transformer. That's the whole problem, is he bought the wrong generator and they sent the wrong transformer. So we're dealing. It'll be next spring or next summer when we're doing it.
I'll just take it back.
Yeah. Yeah. And then they said, oh yeah, and for budget we wanted an idea what's it going to cost to do it. Okay, I've got to look at a bunch of stuff to try and figure out how it's going to happen. But normally transformers are great. You can do almost, if you use the proper channels and equipment, you can get right down to doorbell plug-in. For a security system, sometimes you can get just like a phone charger. You plug it in the wall and it'll give you 24 volts from there. That would be AC to DC. For a phone charger, AC to DC. So the principal operation of the transformer, when magnetic flux is produced by one coil, cuts the conductors of a second coil, a voltage is induced in the second coil. So the primary of a transformer is where the voltage is supplied from your voltage source. The secondary is where that voltage is induced. The process is known as mutual induction and is the principle upon which the transformer operates. So you're applying alternating current to this primary coil here that has the conductor wrapped around, turns around that iron core, and it's laminated just like parts of motors too to reduce eddy currents. And the voltage is induced. There's no physical or electrical connection here. It's just mutual induction creates this voltage on the secondary side of the transformer. So here, an AC source EMF is applied to the primary coil. Varying magnetic field causes the magnetic field to pass through the coils of the primary and secondary coils. An induced EMF is produced in the secondary coil. The magnetic field in the secondary cuts the primary and secondary coils. This produces a back EMF in the primary coil. In this way, power from one circuit can be transferred to another circuit. The coil in which the flux originates is called the primary, and the coil in which the EMF is induced is called the secondary. The amount of EMF generated depends on the relative position of the two coils and the number of turns of each coil. Mutual inductance is the amount of mutual induction that exists between the coils. There's two basic types. One is to increase AC voltage, it's called a step-up transformer. The other application is to decrease voltage, and it's called a step-down transformer. A transformer is designed to deliver the voltage that is required by a transmission system or that is required by electrically powered equipment. Distribution systems commonly use single-phase transformers for light industrial and residential applications. They can convert 220 volts to 110 volts. They're common in industrial plants, supplying 110 volt AC to motor control panels, which distribute power to 110 volt applications, such as small AC motors. Three-phase transformers are used for power transmission. They're seen in industrial plants and substations and switchyards, supplying required voltages for large AC machines. Common voltages used by three-phase motors are 600 volts or 60. American is more for 60 volts. Sometimes even higher voltages, such as 4160, are used. Transmission lines are much higher, such as 138,000 kilovolts, or 138 kilovolts, or 240,000 volts. You'll see on switchyards, transmission stations, even on hydro poles, it'll have plates on it saying what voltage is available on in those areas. Instrument transformers are used to connect meters or instruments to high voltage circuits. They reduce the current and voltage levels which are safe for the instruments. An example would be for instrumentation and power generators and transformers. Hydro One uses instrument transformers for their metering of this electrical service and building. They use current transformers, power transformers that see how much current is being used at the higher voltage, but the lower voltage transformers allow the meter to record what's being used power-wise. Figure 36. Here it shows the arrangement of a simple transformer with two electrically isolated coils wound on a laminated iron core. When an alternating EMF is applied to one coil, that's DP primary, an alternating flux is produced in the core, which induces an EMF, EP, in the primary winding by self-induction, and also induces an EMF, ES, the secondary, in and the other coil is secondary winding by mutual induction. With the secondary open circuited, EP is almost equal to EP, and the primary current is just enough to produce magnetic flux and supply the iron losses in the transformer and very small heating losses. Transformers are efficient. All you get is heat losses. Any transformer that you see is energized, there will be some heat. In a transformer, it can be assumed that all the flux produced by the primary cuts every turn of both the primary and secondary winding, thereby inducing the same voltage in every turn. If the number of secondary turns is greater than the number of primary turns, then the voltage induced in the secondary will be larger than that induced in the primary. This transformer is called a step-up transformer. If the number of secondary turns is such that secondary voltage is smaller than the primary voltage, then the transformer is a step-down transformer. As the voltage in each winding is proportional to the number of turns in each winding, you can use this formula. E primary divided by E secondary equals the number of turns in the primary divided by the number of turns in the secondary. So you calculate the secondary voltage equals the primary voltage times the number of turns in the secondary divided by the number of turns in the primary. And these, so you algebraically change those formulas and use them that way, but we'll see that the turns ratio is easier to use. If you know what the voltage is in the primary, voltage in the secondary, you can calculate the turns ratio when current is proportional to. When a load is connected to the secondary winding of a transformer, secondary current flows and produces magnetic flux, which opposes and tends to reduce the primary flux. This tends to reduce the counter EMF in the primary, allowing more current flow, reestablishing the main flux to its former value. For this reason, the flux of a transformer is virtually constant through all normal load conditions. Modern transformers are very efficient devices, with large industrial transformers often more than 95% efficient. Because primary and secondary power factor are almost the same, and ignoring losses, voltage primary times current in the primary is equal to the voltage in the secondary times power equals power, E times I. The transformer output volt amps equals input volt amps. In industrial transformers, it's usually far more convenient to talk in terms of kilovolt amps or kVA. So another way of looking at it, transformers can be divided into three types: isolation transformers, auto transformers, and current transformers. So what looked at first, that's an isolation transformer. Isolation transformers are characterized by the fact that the primary and secondary windings are physically and electrically separated from each other. The windings are magnetically coupled, not electrically coupled. The primary windings, the windings connected to the power source. The secondary windings connected to the load. So primary is where voltage is applied. Secondary is where you have a light connect over here, or a motor, or transformers operate on the principle of electromagnetic induction. When current flows through a conductor, a magnetic field is created around the conductor. Conversely, when a magnetic field cuts a conductor, a voltage is induced into the conductor. When alternating current is applied to the circuit, magnetic field will continually change in magnitude and polarity, producing a continual cutting action of the magnetic field across the conductor. The amount of voltage induced into a conductor is determined by three factors: The strength of magnetic field, the length of the conductor. This is often stated as the number of turns of wire in coil. The speed of the cutting action between the conductor and the magnetic field in an AC circuit. The speed of the cutting action is proportional to the frequency, which we would see as 60 hertz. When current flows through the primary winding, the magnetic field is created around the winding. The continually moving magnetic field induces a voltage into the winding. This is known as self-induction. The amount of current flow in the primary winding is limited by inductive reactance, not resistance. Inductive reactance is a function of Lenz's law, which states that an induced voltage is always opposite polarity to the voltage that produces it. Induced voltage acts like resistance in that it limits the flow of current. An equal amount of applied voltage must overcome the induced voltage in order to cause current to flow in the circuit. The amount of current that flows through the primary winding when there is no load connected to the secondary is called excitation current. Basically, excitation current is the amount of current necessary to magnetize that metal core. The excitation current remains constant regardless of the load added to the transformer. It is such a small value as compared to the full load current rating of the transformer. It's generally omitted when calculating values of primary and secondary current. That's excitation current. That's not inrush. Isolation transformers operate on the principle of mutual induction. Mutual induction occurs when the magnetic field produced in the primary winding induces a voltage in the secondary winding. The iron core material is an excellent conductor for magnetically coupling the primary and secondary windings together. Isolation transformers has some distinct advantages over other types of transformers. One of these is its ability to reduce voltage spikes in the line. Voltage spikes that occur in the primary side of the transformer are greatly reduced in the secondary side. Some equipment does cause these spikes in your sine wave. Variable frequency drives cause spikes like this. And anytime you're using a variable frequency drive, you would usually have some type of isolation transformer or something they call a choke or reactors. But they do have some kind of isolation between the variable frequency drive and the system so that you're not causing this type of spike in the system when you go through a reactor, through an isolation transformer of some type. This gets changed to just a small one. The transformer has the ability to reduce voltage spikes because it is an inductive load. The current in an inductive circuit cannot increase or rise instantly. The current in an inductive circuit must rise at an exponential rate. Voltage spikes are of very short duration. Since the current generated by the spike has to rise at an exponential rate, it does not have the time required to reach a high potential. Another advantage of isolation transformers is that since the primary and secondary are magnetically coupled and not electrically connected, the load is electrically isolated from the power source. Even if the power source is grounded, the load does not have to be. This can be a great advantage for some types of loads, especially electronic devices, such as measuring instruments like oscilloscopes and recording meters. It's also possible to ground the secondary when the primary is not grounded. A common example of this is an industrial control circuit. Three-phase power is often not grounded. So here you've got line 1, line 2, line 3. But it's desirable to ground the control circuit. So you've got, if this is 600 volts, line to line, 600 volt motor, you take line 1, line 2 to a single phase transformer, and on the secondary, because of the number of turns, you've got, say, 120 volt control circuit. And when you've got 120 volts, You want to ground that neutral. So you can ground it over here for your control circuit. And that's your basic stop-start circuit. Two of those, basically, and you've got your full reverse circuit that we're going to do for the final lab. Several methods can be employed to determine values of voltage, current, and turns of wire in the transformer. One method is to use these formulas, which we looked at before. So in this circuit, the primary is connected to 120 volts. E primary is 120 volts. And the winding contains 140 turns of wire. Number of turns in the primary is 140. The transformer secondary is 24 volts and connected to a load with a resistance of 8 ohms. So the first step is to determine the amount of secondary current using Ohm's law. I secondary, so the secondary voltage, 24 volts, the resistance of the load is 8 ohms. So the secondary current is 3 amps, using that formula. The primary current can now be determined using the proper formula. E primary divided by E secondary equals secondary current divided by primary current. So algebraically, cross multiply the bottom value, one side equal signs, multiply by the top value, and the other side equal sign. Divide both sides by 120 to eliminate 120 on the left side. So primary current is 0.6 amps. So we look at it, higher voltage, lower current, lower voltage, higher current. The number of turns of wire in the secondary can be determined using a formula. And you'll find out that the secondary turns 28. Lower voltage, fewer turns. Another method of determining the values of a transformer is by using the turns ratio. All values of voltage, current, and number of turns are proportional to the turns ratio. Turns ratio can be expressed in a couple of ways. One way of expressing a turns ratio is with a common fraction. So if you have a transformer that has a primary voltage of 240 volts and a secondary voltage of 50 volts, the turns ratio can be determined by making a fraction of two numbers. So the fraction can be reduced by dividing both numerator and denominator by 10. So you have a fraction 24 to 5. The transformer has a turns ratio of 24 to 5. That doesn't mean that there are 24 turns of wire in the primary and 5 turns in the secondary. It's just a ratio that indicates that there are 24 turns of wire in the primary for every 5 turns of wire in the secondary. The number representing the primary winding is listed first. Assume that a transformer has a primary voltage of 120 volts and a secondary voltage of 1000 volts. If both the numerator and denominator divided by 40, the fraction becomes 3 to 25. So the turns ratio is 3 to 25. So the secondary winding will have more turns than the primary winding. This indicates that the transformer is a step-up transformer and the secondary voltage will be greater than the primary voltage. Let's take a